Last week we covered cylinder heads, and we're going to continue along with the induction theme and intake manifolds this week. Now, for your typical V8 application, we've got multiple different types of manifolds, but they're not just limited to V8 style applications. We're going to dive into a whole bunch of different ones and talk about the benefits, where you might want to choose one type of intake over another, and what the power implications of each type of intake are going to be. So that's what we're going to get into. Now, the three main types of intake manifold are going to be a dual plane manifold, a single plane manifold, or an ITB. Now, starting out with the dual plane manifold, what that is referring to is that on a typical V8, we're going to have our 4-barrel carburetor throttle body flange, and that is going to be actually divided in half, where the left side will feed 4 cylinders and the right side will feed a different 4 cylinders, and they are not connected other than they might have some tiny little crossover holes, you know, maybe not even a quarter inch in diameter or something, just to balance the pressure on both sides. But otherwise, basically left side and right side of your throttle body are only feeding an individual 4 runners apiece, and it's not by left side, right side of the engine either. Typically, it'll be where the manifold's going to feed, say, 1 and 5, 4, and 8 as far as the cylinder numbering is, if we've got an engine that's 1, 2, 3, 4, 5, 6, 7, 8 like this. And what it's just trying to balance it side to side on the engine. Dual plane manifolds are typically better at building low end torque, just because the way that they end up routing and, you know, crossing it over, it really limits the size of the runner, so it keeps the runner small and keeps the velocity up. They work great for carbureted applications, for a throttle body fuel injection style where the injectors are in the throttle body. They're not a good manifold for that application, and it's just because of how many turns it takes to get to the cylinder, because like we talked about in the cylinder video, air does not like to go around corners, and fuel atomized in that air even more so doesn't like to go around corners. So by the time a dual plane can get the air and fuel to the cylinder, it's changed directions so many times, it just doesn't work out really well. And for some reason, it's fine with a carburetor. A carburetor might be doing a better job of atomizing the fuel and letting it carry all the way, versus a throttle body injection style. There's just not as well. They don't keep a very good cylinder balance. And by cylinder balance, I mean, like, you can pull spark plugs and see the different air-fuel ratios that one set of 4 is running at versus the other set of 4. And that is still evident when it's a carbureted application, but it seems to be less so. Now, the dual plane manifold is not limited to V8s. You can also have inline 6s that have dual plane style manifolds, or a V6 style, you know, still thinking more American style engines. You can also, they're not limited to just a single 4-barrel either. You can also have a dual 4-barrel setup, where at which point you've got 2 cylinders, like, per primary barrel being fed off of each carburetor, and it's just the style of the manifold. And then same thing there's probably a couple of holes for balancing the pressure, because balancing the pressure out plays into trying to get the engine to run consistently. If you ever messed with like 2-cylinder motorcycle engines and stuff where they've got, you know, individual carburetors, you'll know that trying to balance out the pressure between the throttle body and the engine, having those pressures balanced helps the engine run smoother. Same deal there. That's why those holes are drilled into the bottom of a manifold on just like a little tiny crossover tube to try to balance out the pressures to make it run more evenly. It's not actually really transferring any fuel or air. It's just about getting the pressures even. Now, single plane, we've got several different styles of manifold that can all be single plane. Same thing, we can have our standard single 4-barrel, in which case the entire plenum underneath is open. All of the cylinders all feed off of the same area of air volume below the carburetor. So this is our carburetor up here, or our throttle body, either way. Our intake manifold is going to be whatever, like this volume in here is shared between all cylinders before it divides into individual runners. And it might be close up top, it might be farther down. It really doesn't, it just depends on the actual intake manifold itself. They can be short, low rise, they can be tall, high rise ones. There's all kinds of different variations of this. And then you also have your dual quad, so that'd be 2 carburetors, and a single open plenum in there. And along that lines, we also get into taller manifolds like a tunnel ram, in which case this gets a lot higher, where we've got our carburetor up top. We've got, a manifold like this, and then we've got really big individual runners. They're, tall, big, tall compared to the height where, this style manifold's probably only going to be about here, but now we've moved our carburetor way up. Those runners, they get longer, and if we're looking at it from the side, like here's our flange to the cylinder head, we're talking about a manifold that might come up like this. And we've got our carburetor, so our runners are just like that up into our plenum, versus moving that carburetor up much higher and having a big straight shot kind of a thing for our runners. Now, obviously, going to a tunnel ram, the straighter we can make these runners, the more power potential we have, because the air isn't changing directions as much, and it can flow more evenly and in a straight line because it doesn't want to change directions. These types of manifolds, also getting into a tunnel ram or some kind of high-rise setup, we're adding runner length. And runner length comes into play when we're talking about the pulse tuning of an engine. So if you're paying attention in our cylinder head class, we talked about air moves through an engine as AC current does, like electricity. We're going from the carburetor towards our runner, and then we go back a little bit, and then we go towards our cylinder head and back a little bit. We're going towards our cylinder head, and we're going back a little bit. And this is because if we didn't have valve train in our engine and it was just an open hole and we could somehow still pump air through it, it would just be moving in a straight line. It'd be no different than taking a cardboard tube and blowing through the end. Air is just in a straight line, nothing's in the way. But now if you take that same cardboard tube and you're blowing in the end and you start slapping your hand against the back side, it builds pressure inside of that tube and it bumps back against your face. Well, same thing's happening when the intake valve is opening and closing. The air moves, it closes, it makes a pressure spike at the valve, which then sends a pressure wave back up the intake runner. And at some point, that's going to turn around and go back because the valve's going to open, air's going to start flowing that direction again. But what's happening with adding our runner length is, much like what we're going to get to with the ITBs, is we're tuning an RPM range out of that runner length, because as the air comes back into the plenum, it can either cross feed and come out of one runner and go into another to make a little bit of a self-supercharging effect into a different cylinder, or it can come back up, bounce off of the plenum area, and self-supercharge the same cylinder. But in a normal, typical style intake manifold, we're going to be talking about cross-talking between cylinders versus a tunnel ram. It kind of spreads everything out. There's still going to be some cross-talk, but it might be more into its own runner. Or if we're talking more about an inline style intake manifold, where say we've got a throttle body out on the end, and we've got our runners coming straight off, where that pulse comes back, bounces off the plenum, and goes right back into the same cylinder. And that pulse is obviously not traveling in a straight line, because as soon as it gets into this big area, it's going to just, spread it out, kind of a thing. But we've got all these pressure cycles happening inside of the intake manifold, and this is where, if you're trying to be clever and science this out with some kind of software that talks about, airflow and potential, like trying to design your own intake manifold, unless you can do a setup that, number one, can handle having flow out of individual runners with a single inlet, that's the first place to start, because I've seen a lot of simulation softwares where people are trying to do it off of one inlet and one runner at a time and just make all the runners balance out. Well, that's not what's actually happening in a running engine, because it's pulling all six. If it's an inline six at the same time, or all four, or all eight, or whatever. So that software really is not even close to being representative of what's actually happening. Simply because if you're having one supply in and only one out in that flow software, then you're completely missing out the fact that it's actually not pulling one, it's pulling 4, 6, 8 times as much out of different places, and it's going to cause all kinds of different airflow turbulence and vortices and everything else inside that intake manifold that it's just not accounting for. And this is where you get into these style manifolds where they're front feed, and especially in a boosted application, it just rams the air right through. The back cylinder gets all of the air, and it's really hard to get an even amount of air in the other cylinders, because there's just, they're all seeing the same pressure, but the actual air flow through the manifold is different between cylinders. Now, if all of this pulse tuning in the intake manifold is not anywhere more evident than in an ITB setup, because at this point you've got your cylinder head and we've got our runner. Just gonna draw it straight. I mean, it could be any kind of different curve shape, whatever, up to our throttle body. And this distance becomes so important, because we're getting that pulsing through the system, and there's what's referred to as a first wave, second wave, third wave is usually the ones you look at, and that's just referring to how many times that pulse moves back and forth before the valve opens again, because yeah, it's moving that fast. So with the ITB, the pulsing, coming off of our valve is going to be traveling all the way out, and if we're you know, I got this part throttle closed there, but if our throttle blade is wide open in here, then the pressure waves are actually going all the way out and they're into the atmosphere. And the reason that this runner length or pressure wave tuning is so important on ITBs is because it does not have a common plenum. That common plenum enables an intake manifold to do that cross-talking between cylinders that I was talking about. And it gives the advantage of letting one cylinder help another at different harmonic ranges. I mean, and by harmonic ranges, I mean RPM range. Because the RPM changes the harmonics of those pulses inside the intake manifold. So because, you know, a runner length that, say we're wanting to tune for 6,000 RPM. Well, what is the optimal or possibly ideal runner length for 6,000 RPM is not the optimal or ideal runner length for 5,800 or 62. It might be pretty close still, and it'll probably work pretty good, but then it's gonna work even less well at 5 or at 7? Well, a single plane manifold where it's able to let that cross-talking happen, and even in a dual plane manifold there's that cross-talking happening, although, you know, limited to the cylinders on that bank kind of a thing, or in that side of the manifold. It lets it kind of balance out where we can make a more even power curve out of it, versus an ITB does not have that benefit. So typically you'll end up seeing on a lot of ITB engines, if you look at their dyno graph, so they've got kind of like steps or even dips in it. And that's like where at this RPM, and this RPM, like that might be our first, second, and third pressure waves, where they start lining up nice to make power. But then our dips are where that pressure wave just kind of falls out of being optimal, where instead of the pressure wave coming back and being right on top of that valve when it opens, ready to go and give that self-supercharging effect, it's going the wrong direction, or it's not there. And instead of that pressure wave being there and ready to go in the cylinder, the pressure wave's off somewhere else, and we're not getting that added benefit. And we could even be having where the pressure wave's moving in the opposite direction of where the airflow needs to be going, and we're kind of like canceling out some of the airflow just because of that pressure wave moving in the wrong direction. And this is why it becomes so important with ITBs, especially when you're building a race engine, that say we're wanting to target this window of RPM. Well, we can tune the length of this runner along with using a dyno to test it, although there are formulas out there to get you in the ballpark online. I believe Wallace Racing Calculators is the one I've seen. And that'll help you like figure out what this length is. And because of the different pressure waves there, we could have a really long runner, one that gets us in our window, or we could have a medium length or even a short length that will still get us into our window. And at that point, it kind of depends on packaging as well. However, overall, the generalization is the longer the runner, the more lower end and mid-range torque the engine is going to make, which is why tunnel rams do so well at that. They're a nice big straight runner to make high RPM power, but because the runner is so long, and as long as the runner isn't too big itself, it builds good low-end torque too. One thing you might not know is that intake manifold runners have taper built into them. Now maybe there's a couple instances where they don't, but there's almost always taper. Now what this taper is doing is, again, it's taking a larger volume of air and we're putting it into the cylinder head at a little bit smaller volume. So what we're doing is we're trying to accelerate the air as it moves through the runner, because if you've got X amount of volume of air here and you squeeze it down a little bit, well, to move that same volume of air, keep that same volume of air moving, it has to move faster at this end than this end in order to maintain that volume of air being moved. I think the typical number is like 3 to 7 degrees of taper. And that's just a general rule of thumb thing. If you were trying to design an intake manifold from scratch and wanted to optimize it, you really have no choice other than to do dyno tuning, because again, the dyno is the final word. The engine will tell you whether it likes something or not by making more power or less power. And usually an intake manifold, it can either be that taper in the vertical range or side to side. It could be a little bit of both. It's just kind of a general number there. But the big thing is that the taper is there. So if you're trying to build one from scratch and you just want to, say, take a 2-inch round tube and make that, and it's just dead straight, it's not going to be as good as if you had taper in that runner. And you could easily do that into that 2-inch round tube if you put a slit in on both sides and just expand it, and maybe it'll be an oval on one end and round on the other if your cylinder head is round, or you'll have to shape it into a square. You'd have to figure it out if you're customizing and building something like that. The next part would be where our runner meets our intake. Because air doesn't like to change corners, radiuses, the bigger the better. A little radius like this be just fine. A much larger one would be even better. And again, you're going to have packaging constraints and everything else. And this, drawn out kind of tunnel ram like here, obviously it's going to come down to packaging also, as far as what fits under the hood. What space do you have available in an engine compartment? You're going to have lots of limiting factors in physical space where you're just not going to be able to design the most perfect optimal intake manifold. Unless you have, it's almost just out in space and you've got all the room in the world kind of a thing. Now the reason the radius is so important is to promote airflow into the runner. So if we've got our runner and we just have sharp corners into our plenum, the air, it can go straight down, but the air coming from the side can't just pull a 90-degree corner. So what happens is this air comes across and gets thrown out and ends up doing something like that on both sides, which ends up being a complete loss of airflow in these areas. It can't fill those voids because of that sharp corner, and air is just like jumping off a cliff kind of a thing. It doesn't fill those areas, and we've effectively choked our opening, where the air we should be able to fit through that opening just doesn't happen because of the choke point. Now if we radius our corners, we've made it much easier for that air to stay attached to the sides, and we're now utilizing all of that opening and getting as much air through that as we can. This is the big reason why velocity stacks are important on ITBs. And if you're just running say a turbo with a screen on the front and absolutely nothing, you're getting less airflow into that turbo than if you had a velocity stack on it, because of the same reason here. It's just, it's pulling air. And the reason is because if we do say we extend our runner into our plenum. So we've extended our runner into our plenum space. The reality of this is that we've got our air still coming straight in, no problem. But how air actually acts when we're creating a vacuum here is it will pull air from down here all the way around and back in. This is one reason why when flowing a cylinder head, they always put clay around the opening. It's because it's pulling air from flat against the flange surface up over that clay the entire way, versus if you had no clay, it'd be the same thing. It's pinching down that opening and restricting airflow. And when you're doing it on a flow bench there, I mean, you can start seeing it at as little as a quarter or 300 of lift. Like, not even flowing a very much air compared to what the cylinder head can be capable of, and it already starts to restrict it because of the sharp corner. And I always thought this was a super interesting thing about how you can have a velocity stack like this if you ever put it on a flow bench, and you can put your hand down here behind the velocity stack and you can feel the air going past your fingers as it gets drawn into that velocity stack. It's actually pretty cool. But this applies to everything about our induction system. Is you need to have radiuses on stuff, because that promotes getting the most amount of airflow and creating the smallest amount of restriction to it along the way. Another good example of this is even like the air cleaner base. You know, if you've got an air cleaner base going into your throttle body that's got these sharp corners, or a very tiny radius at best, it's really kind of a crappy air cleaner base, versus having one that has more of a big radius shape like that. And it's because this big radius shape like that, actually, by the time the air starts going into the throttle body or carburetor itself, it's already traveling at a much higher rate of speed by the time it gets here than it ever does going off of this sharp, tight radius. Enough so that this air cleaner base, I've done back-to-back dyno tests with one like that, and the sharp corner air cleaner base, usually say down, like actually down on power compared to no air cleaner, by anywhere from 8 to 15 horse or more. The big radius air cleaner base with an air cleaner still would actually be, I've seen 3 to 5 horsepower more than using no air cleaner at all. So that's super interesting, but it's the same. It's because of the way the air is flowing and about promoting a high airspeed as it enters the carburetor or throttle body. Now these two intake manifolds are, or rather were at one point in time, the same manifold. Obviously this one's been heavily modified, but it started life as this exact same manifold. Ignoring the cooling mods and stuff, it should become pretty evident when looking down in the plenum areas just how different these really are. Now, largely, the runner sections here between the two manifolds are going to be very close to each other still. The big modifications are this one's got a spacer welded onto the sides to make it fit a raised runner cylinder head versus the stock style. This manifold is still set up for a 4150 flange, so the smaller opening versus the Dominator flange. The big obvious radius up here at the top, that is for anti-reversion versus just being a straight opening, where this sharp corner here really doesn't matter because the barrels of the throttle body are inside of the opening and they've got sharp edges on their bottoms anyway. The anti-reversion is to those pressure waves coming back up through the intake manifold that we talked about. We're wanting to dissipate them below the carburetor, so we give it this volume of space for it to kind of get lost. And what that does is it actually creates a lower pressure area right below the carburetor, which actually helps with drawing more air and fuel at idle and in cruise kind of a thing, because it's giving a better signal to the carburetor. The other reason for doing this is it helps keep those pressure waves from traveling up through the carburetor and basically getting above the carb and then going back through the carb as the air is switching directions and resulting in what's called double carburation, where actually the same air ends up getting 2 times the fuel because it's gone through the fuel atomization process twice. Now, even on the smaller manifold, you can see I've gotten in there and we've opened up the radiuses quite a bit, especially at the top edge of the runners. And that's, again, just to try to straighten out what that air has to do to get down to that cylinder. Versus with the larger flange, we can be a lot more aggressive about it too. And it's become a much, much larger radius by comparison. Also, it's pretty easy. You can see how much opening we have looking down the runner, that it's pretty much, once it makes the turn, it's a straight shot with air and fuel. Versus there's still some we can see down there, but not quite as much. Part of that's due to this spacer, but again, the spacer is here modifying our plenum volume because this engine wants plenum volume. We've obviously got a lot more of it in this manifold as well. Actually, this used to be another inch taller, and we found on the dyno that it didn't change in power cutting it down. So we were able to get away with, well, we finally got to where we knew we had enough plenum volume for the engine by testing it on the dyno that we were able to take a spacer out and see that it was happy, and we were able to cut this down and shorten up the manifold a little bit, where in reality, the height of the manifolds is not all that much different. This one's actually quite a bit taller, since it'd have to come up to kind of equalize on where it sits on the head, just because this one's added down here because it's for a raised runner. And if we look at this part of the manifold as well, you can see that's been heavily modified. Actually, what I did was I cut a half round piece of aluminum tube and then welded in there. And again, that's to open up the plenum volume, because this manifold does not have enough plenum volume. What it also does is it basically moves that out to here. And what we're doing is we're making our short runners versus our long runners, because like we talked about the wave tuning, about how long that runner is, it's obviously different between these two runners. Well, by adding plenum volume out here, we're actually shortening the long runner and we're getting these closer to equal length. So where they leave the plenum at, if we cut that like there, that's a lot closer in length than on this side where it's like that. Which again kind of plays into why a tunnel ram actually works really well, is the runners are equal length. right off the bat, because they're just a straight shot off of the head up into a large, big plenum volume area. Most engines like plenum volume. You know, it can be a give or take. Like I said, we found a place on the dyno where this manifold had too much plenum volume, or it had enough that it didn't care. When we reduced the plenum volume, it still made the same power. So we were able to cut the manifold down, make it shorter. It's better for packaging under a hood. And we didn't hurt the performance of the engine because we had enough plenum volume. Versus that intake manifold there, we can run on the dyno without the spacer, and we can add the spacer, and it picks up power with the spacer because it doesn't have enough plenum volume in that manifold on its own. Now if we compare to yet another single plane manifold for the same engine application, you can see just how much more of a, you know, this would even be considered a mid-rise manifold versus a low-rise, because like factory manifolds, the carburetor flange is probably the same height as the water neck area here. But you can just see how much less volume there is in there, and how the runner entries are different. There's almost no radius on this top edge. So when the air and fuel comes out of the carburetor, like it's almost doing an immediate 90-degree angle. It's just, I mean, this, don't get me wrong, this is still a pretty dang decent street manifold. I'd run this on a street application that's say 6,000 RPM. At the high side, it just, you know, max for an engine. This is a great manifold for that, actually. And because it's a single plane, I would use this on a throttle body fuel injection setup over a dual plane any day. Just because at least this is going to have a much more evenly balanced air-fuel ratio to all the cylinders. But as far as high RPM performance or big displacement and actually moving a large volume of air, it's no comparison compared to the larger, straighter runner, bigger plenum volume manifolds as far as the power potential and the RPM potential of the engine that it could go on. So what's going to be the right intake manifold to choose for your build? Well, much like everything else along this journey it depends. But we can go with some generalizations on things. Now, our dual plane, honestly, I don't like them simply because of the fuel distribution side of things. However, if you were fuel injection and had the injectors in the manifold on the runner instead of a throttle body setup, this would be a more viable option. I still don't like it because in my experience, the balance of airflow between the two sets of 4 cylinders isn't very close. I mean, at least not when you add fuel to it and you can see how the mixture is burning, because usually 4 will be a little bit lean and 4 will be a little bit rich, kind of thing. So I'm not a fan of these manifolds because of that. However, if you're looking at a dual plane, typically you're going to be somewhere between stock to mild build or some kind of like a towing application, something like that, is really where the bread and butter of these manifold styles is. They're not going to make big RPM. They're not going to make big power. It's just the limitations of the manifold itself. Now, if we go into a single plane, obviously we've got the whole wide variety, as you saw, of options for even a single engine application that can be done with a single plane. And really, a single plane is not a bad choice for pretty much anything. If you're putting it on a completely stock engine, it's probably maybe not the best choice, but if you plan on modifying that ever in the future, it's probably a better choice for as far as you know, giving yourself room to grow with the engine. So I'd really start here with you know, anything mild and up. The single plane's probably going to be a decent choice, and within that category is bigger displacement, higher RPM, or higher horsepower are all going to lend themselves to being a bigger single plane intake manifold. Bigger, I mean, really we could just call it with height, like a pretty mild one. I mean, a short height manifold, like the third manifold I showed you, would be just fine, versus going in this direction, it's going to be a taller manifold. And that's just kind of where we're at with that stuff. You're also going to have to look at, especially when you start getting into different aftermarket race style heads, that you're going to see that the dual plane completely is gone. It's not even an option. You know, your single plane manifolds are going to go from, you probably got every possible option in the world for a 23-degree head small block Chevy. But as you get into race heads, like an 18-degree or 14-degree or whatever other variation of that, the amount of manifolds to choose from is going to get smaller and smaller. And that's kind of a natural selection of making sure that parts are going to work together. I mean, really, it becomes kind of easy at that point when you start hitting certain power goals with certain applications, where it's just like, well, like, these are the parts that fit together, and these are your options, and that's what's going to get you into this power range, because that's what the parts are built for right from the get-go. Versus it's a lot more difficult if you're working around stock style stuff, because you almost have too many options. Now, as an example for me, my Oldsmobile stuff, like I've got these 3 manifolds there. They're all for a small block Olds, and yet I had to modify the Big Victor so much farther, as you could see, because I modified a set of heads into raised runners in order to make more power, and then I needed to modify an intake manifold just to fit at that point in time. And then, as long as I was already modifying the intake manifold, I did all the plenum volume modifications. And at the time that I did that Dominator flange, you couldn't buy a Victor with a Dominator flange, so it just was a matter of turning it into making my own part to fit the bill, because that stuff wasn't available. Not going to be the case if you've got a very common engine platform, but at the same time, it's just a matter of finding the intake manifold that fits your application. And again, with the single planes, even if we're trying to do a big displacement, higher RPM build, taller manifold, well, at some point you're going to have hood clearance issues that you may or may not be willing to put a giant cowl hood on. And it's just a matter of, making those choices so that the end product is something that you actually want. And in the case where I put the spacer on, I had the cowl hood and the hood clearance to put that spacer on without any consequences to me doing it. So I'm going to take that free, 10 horsepower or so by adding that spacer, because I didn't have any physical limitations on being able to do so. Now the flip side is I had that spacer on the shorter style manifold on a stock hood car, and that forced me to pick a shorter air cleaner, and that comes into play too, because like you talked about, you have that big radius base air cleaner, it's really good. Well, if the lid ends up being pinched really tight to it, we're still not getting all that much air, even though we're getting the benefit of the base. Yeah, so there's a trade-off there where, I chose to run the spacer to help, make the radius bigger into the runners and a little bit better air-fuel balance on that short manifold. As a trade-off to, I ended up restricting it a little bit at the air cleaner because it got tight to the hood. And I mean, that's a trade-off. It was a choice I made. I never dyno or chassis dynoed the car to really know if there was a power benefit one way or the other. That would have been the right way to do it, but I didn't have the time or the availability of a dyno right around the corner to do it, kind of a thing. But it's a choice that needed to be made, and it was a compromise that I made. Alright, now I feel we can't finish out the intake manifold video without kicking some LS guys in the nuts. And that being referring to the fact that it seems like everybody and their brother wants to run a Holley high ram. Now, the high ram is a tunnel ram style intake manifold, like we've talked about. There's actually a lot of benefits to it. However, the caveat of that is we're not comparing it to a stock intake manifold or a even aftermarket dual plane or single plane manifold for a small block Chevy. And the reasoning being is your stock LS manifold has your throttle body at the front. And we've got our cylinder head over here. We're not going in a straight line. And it's going to be a little bit of a bender, but here it actually has a runner on it like this, where we are cross-feeding from the opposite side of the engine into the cylinder head. And in some cases, that actually can even wrap around the top a little. And what's happening here is we are building a ton of runner length into that manifold, or rather GM built a ton of runner length into that manifold right from the get-go, and still kept it short, low profile, clears Corvette hoods, kind of a thing. And what they're doing with that runner length is they're making a runner that, number one, long in length, so we're benefiting low and mid-range torque. Two, they can actually pick the length of the runner to the point where they're actually tuning the pulse phasing. And what the result is an intake manifold that comes on, builds really good, meaty, fat mid-range, and then kind of slowly falls off towards the higher RPM. Just big, fat torque curve. We're talking from here to here is probably 3,000 to 6,000. Like good, big, fat mid-range. And then guys go and put a Holley high ram on it. And it's got this short little runner in it. And that ends up doing this to the dyno curve. Might start out pretty close, and it's just like, oh look, I made a little more power. And it might not even, it might only be 1,000 RPM because they didn't change anything else about their engine. They didn't up the compression. They didn't put a big cam in it to make it build power up here. All they did was stick that intake manifold on. And they threw away probably 50 plus foot-pounds in the middle over this big RPM range to get 10 to 20 horsepower on top. This is a horrible decision. Horrible. I mean, unless you got an engine where you're only between 6,000 and 7,000 RPM for the entirety of its use, then okay, yeah, you made better power in the spot you're using it. Meanwhile, everyone else that drives their car, drifts their car, does road course, anything else where you're in this RPM range, the factory intake manifold is so much better. So much better. And this is a great example of putting the wrong parts on that don't match the rest of the engine and what it does to the power that that engine makes. So all that being said, what would be the best intake manifold for what I build as far as road racing stuff? Honestly, I'd like a stock LS intake, but they don't make this anything even close to that for an Olds. And as much as I want to build my own intake along those lines, it is a huge undertaking to try to build an intake manifold from scratch. And that would eat up a lot of time that I just don't have right now. But I might get to it one day. And instead, I'm just, working with the best manifold that I can use at this time, which is that Edelbrock Victor with the spacer on it, because that's the one on the car. The other heavily modified one is for my other engine. That's going into the tube chassis that you saw in the back of that clip that I'm in the process of building. And part of those two manifolds being so drastically different is the tube chassis car is getting an engine that's 80 cubic inch larger and has probably another 5 to 1,000 RPM on the top end, along with a much, much larger cam. So that's where the difference is in those engines. The needs of each engine is completely different, and that's why those manifolds are so different. And just like me having to make a choice about it, so are you. Like, you're going to have to weigh all of your options about what's available, what might be a good fit, and what are your goals, whether it'll even fit in the vehicle. All of these things need to factor in to choosing the correct manifold for you. Then there's also your budget to figure out, because of the manifolds I got sitting over here. Like, I bought that short mid-rise intake with an entire engine attached to it for, what did I pay, $120? I mean, the intake's worth that. The person just wanted to get rid of the engine. So I bought the whole thing. And honestly, for the shape of the engine, it looks like the timing chain was all wore out. I could probably put a timing chain on it and it would run. But neither here nor there. The flip side is that Edelbrock Victor intake, I think the prices are almost up to, I think they're 700 something now. I remember 10, 15 years ago when they were 350, but it's just, it's the way things are going with pricing. So when you start looking at, doing a street build, if I was doing a street build and I had a cowl hood already and the Victor would fit, be like, do I have that extra $600 in my budget or don't I? Because that's a pretty big chunk of change when it starts coming to an engine build, and you're talking about a build that's going to be, $6,000 to $10,000, $15,000, $20,000. It all, it's all relative about what your goals are. So that decision needs to be made. And if I was on a budget, there's absolutely no way I'm buying a brand new Victor for an engine. I'm going to look for a used manifold that I can get, or just something that's half the price that's not as good of an intake, but it's still a good intake. And I can always take that lesser intake and I can get in there with a grinder and I can do a little porting to it and I can make it a little bit better. It'll still never be in the same ballpark, but it's still better enough where, you know, I spend 2 hours grinding on it and I can probably find another 10 to 15 horsepower. You know, it makes it, well, I mean, if that's my budget, hey, the grinder time is, you know, essentially free if you're doing it yourself. That's going to be it for the intake manifold video. The next up is going to be headers. It'll probably be a little bit shorter video, but I think at the end of the header video, we're going to look at the intake manifold, the cylinder head, and the header, all as a package deal, because we need to know, or we need to understand how they work together and what that's doing as the air moves through the engine, especially with how it ends up playing into our camshaft as well. So we can look forward to that in the next video.